The manufacturing process of straight seam ERW pipe piles at Atlas begins with hot-rolled coil steel. This raw material undergoes a rigorous quality assurance process to ensure that it meets the required standards. Experienced technicians at Atlas test the incoming steel coils for their tensile properties and yield strength. These tests determine the steel's flexibility and overall quality control. Once the coils pass the quality checks, they are slit to the appropriate size based on the desired pile diameter for the specific production shift. Slitting the coils involves cutting them into narrower strips. This step is crucial as it prepares the coils for the subsequent stages of the manufacturing process. The slitted coils are then loaded onto the tube forming line. The tube forming line is where the actual production of the pipe piles takes place. Here, the steel is uncoiled, meaning that it is unwound from the coil and then flattened. The uncoiled and flattened steel is joined to the end of another coil through a butt weld. The butt weld is an important aspect of the process, as it ensures a secure and reliable connection between the coils. However, before the welded portion is incorporated into the pipe piles, it undergoes a meticulous inspection. If any defects are detected, such as welding imperfections or irregularities, the welded portion is cut out and discarded to maintain high-quality standards. The continuous sheet formed from the joined coils then enters the production process. To ensure full traceability, the heat number of the steel used is permanently engraved in an ID stamp on the inside of the pipe. This heat number serves as a unique identifier that enables Atlas and their customers to track the steel's source and manufacturing date. Additionally, the heat number is stenciled on the pile's exterior after it is formed, further enhancing traceability. The facility at Atlas operates with well-established procedures and reliable equipment, enabling them to expedite the production and shipment of the pipe piles. An accumulate, or storage mechanism, is used to store up to 4 coils. This ensures a continuous supply of material throughout the subsequent stages of the process, eliminating any interruptions and maximizing overall efficiency. By implementing these steps, Atlas ensures that their straight seam ERW pipe piles are of top quality, traceable, and ready to provide strong support for deep foundation projects. After the completion of the ERW welding process, any excess seam from the weld is carefully removed using a scarf cutter. This step ensures that the pipe has a smooth and nearly invisible seal, enhancing its overall appearance and structural integrity. The pipe is then subjected to an ironing process while it is still hot. This ironing process helps achieve the desired size and diameter required for installation. To ensure the weld integrity and detect any potential internal flaws, the pipe piles undergo ultrasonic testing. Ultrasonic waves are passed through the pipe, and any anomalies or defects in the weld are detected. The pipe piles are gradually cooled down using a constant stream of water and coolant. This gradual cooling process is essential to prevent any potential cracking or splitting of the steel due to rapid temperature changes. Turk's heads, specialized tools, are then used to work the pile to its final precise size, ensuring accurate dimensions and a superior surface finish. Before the final cutting stage, the heat number that was initially engraved on the inside of the pipe is stenciled on the exterior. This heat number serves as a unique identifier and allows for complete traceability throughout the manufacturing and supply chain process. In order to guarantee the integrity of the pipe piles, they undergo 2 destructive tests. The first is the code test, where hydraulic pressure is applied to the pile until it fails or expands to a predetermined amount. This test verifies the weld's integrity and ensures that it can withstand the expected loads and pressures. The second test is the flatness test, where a sample of the pipe is flattened in both vertical and horizontal axes. This test verifies the weld's integrity and the ductility of the steel itself. To maintain meticulous documentation and quality control, every Atlas pipe pile is barcoded and accompanied by an original mill test report (MTR) from the producing mill. These reports, along with coil certificates from the steel supplier, undergo thorough review before the coils are shipped to Atlas plants. The raw materials required for PVC pipe production are delivered to the manufacturing plant via rail cars and trucks. These materials are stored in silos or rail cars located near the plant facility. The primary ingredient is PVC resin, which is blended with 5 to 8 different raw materials depending on the specific application and industry standards. In the blending room, the raw materials are stored in separate microhoppers. Higher usage materials like resin and calcium carbonate are stored in silos and vacuum conveyed into the mixer system. The materials are carefully blended together in both hot and cool mixers using paddles and blades. The blending process ensures a uniform mixture of the raw materials. After the blending process, the mixed compounds are transferred from the holding silos to hoppers positioned above the extrusion line. The powder compound is gravity-fed from the hopper into the extruder. Heat stabilizers and lubricants blended into the compound help it move through the equipment smoothly. The extruder consists of a barrel, screws, and a motorized drive system. The compound enters the extruder and is compressed and heated by the screws, transforming it into a hot and pliable material. The extruded PVC material passes through an extrusion die, which consists of several components held at precise temperatures above 300 degrees Fahrenheit. The die culminates in a sizing sleeve that determines the outside diameter of the pipe. As the PVC exits the sleeve, the speed at which the pipe is pulled determines the thickness of the pipe wall. This control ensures that the inner and outer diameter of the pipe and the wall thickness meet specific industry standards. After exiting the extrusion die, the hot PVC pipe goes through a crucial cooling process to stabilize its shape and dimensions. The pipe is passed through a series of cooling tanks that are specifically designed to spray chilled water onto the material. The chilled water helps to rapidly cool down the hot PVC pipe, allowing it to solidify and retain its desired shape. The cooling tanks are strategically designed to provide efficient cooling while maintaining the structural integrity of the pipe. These tanks are equipped with spray nozzles that uniformly distribute the chilled water over the surface of the pipe. The water absorbs the heat from the pipe, rapidly lowering its temperature. One significant aspect of this cooling process is the use of recycled water within the plant. The water used in the cooling tanks is processed and recycled, reducing the need for excessive water consumption and minimizing the environmental impact of the manufacturing process. To ensure uniform cooling and consistent wall thickness, a puller is employed in the process. The puller controls the speed at which the pipe moves through the cooling tanks. By maintaining a precise speed, the puller ensures that the pipe remains in contact with the chilled water for an appropriate duration, allowing it to cool evenly. This controlled cooling process helps to prevent any deformities or inconsistencies in the pipe structure. Once the PVC pipe has been cooled and solidified, an inkjet printer is utilized to imprint specific manufacturing information on the surface of the pipe. This information serves as a unique identifier and allows for easy tracking of each individual pipe. It includes details such as the pipe's dimensions, production date, and other relevant data. A carbide tip saw blade. This ensures that the pipe is prepared for installation in accordance with industry standards. Additionally, the wall thickness of each pipe is carefully measured to guarantee superior quality and consistency. These measurements are wirelessly transmitted and stored in the production records, providing comprehensive documentation of the pipe specifications and enabling traceability throughout its life cycle. In order to ensure a secure and tight fit between the pipes, a gasketed bell is formed on one end of the PVC pipe. This process involves heating the end of the pipe to make the PVC material pliable and easier to work with. The pipe is carefully rotated during this heating process to maintain a consistent temperature around its circumference, ensuring uniform pliability. To shape the gasketed bell, a mandrel is utilized. The mandrel is a steel form specifically designed to create the proper shape for the bell. Before the pipe reaches the mandrel, a rubber gasket is loaded onto it. The gasket serves as a seal between the pipe and the joining components, ensuring a watertight connection. Once the pipe reaches the desired pliability, it is pushed onto the mandrel and over the rubber gasket. The pressure applied during this step allows the bell shape to be formed around the gasket, creating a secure joint. The gasket provides superior resistance to difficulties that may arise during the construction process, such as ground movement or external pressure, maintaining the integrity of the pipeline. It is important to note that Diamond Plastics Corporation utilizes a gasketing system called a reboot system for their PVC pipes, which is considered one of the best joining methods in the industry. The use of this system ensures a reliable and long-lasting connection between the pipes, enhancing the overall performance and durability of the pipeline. The heating and gasketing process takes place in a controlled environment within the manufacturing facility. The temperature and timing of the heating process are carefully monitored to achieve the desired pliability without compromising the structural integrity of the pipe. The result is a precisely formed gasketed bell that meets industry standards and provides a secure joint for the PVC pipes. After the gasketing process is complete, the pipe moves to the quality assurance stage, where it undergoes various tests to ensure it meets the required specifications. The gasketed bell joint is inspected for its proper formation and functionality, further ensuring the reliability and performance of the PVC pipe manufactured by Diamond Plastics Corporation. Quality assurance testing plays a critical role in the manufacturing process of PVC pipes at Diamond Plastics Corporation. Apart from the online hydro testing conducted during production, the company conducts several additional tests to ensure that their PVC pipes meet the stringent industry standards for durability and reliability. One of the important tests performed is the impact strength test. This test assesses the ability of the pipe's wall to withstand impact by subjecting it to the force of a 20 or 30-pound weight. The weight is raised to a specific height and then dropped onto the pipe wall. Any cracks or breaking observed in the pipe would indicate a failure, highlighting the importance of its impact resistance. Stiffness testing is another crucial evaluation conducted on the PVC pipes. This test determines the vertical load pressure that the pipe can withstand to meet industry standards. A sample of the pipe is loaded into a test fixture, and a hydraulic press applies downward pressure at a prescribed rate. The load applied to the sample and the amount of deflection are measured, allowing for the determination of the pipe stiffness, particularly significant for sewer pipes. To assess the pipe's resistance to deformation, flattening testing is performed. In this test, a sample of the pipe is hydraulically flattened to 40% of its original diameter, or deflected by 60%. The PVC pipe is capable of flattening until the opposite sides of the wall touch. After the pipe is removed from the flattening process, it is checked for any cracks or breaks in the material, which would indicate a failure. Fusion testing is conducted to ensure proper fusion of the PVC material during the extrusion process. A prepared sample is immersed in an acetone bath for 20 minutes. The process begins with cutting and pre-tensioning the PC pre-stressed concrete bars, which will form the reinforcement cage for the spun pile. The PC bars are cut to the desired length and then welded together to form a cage. This cage provides the structural strength to the pile and helps it withstand the loads it will be subjected to. Once the cage is ready, The next step is concrete feeding. A concrete admixture, which may include additives such as plasticizers or superplasticizers, is added to the concrete mix to improve its workability and strength. The concrete is then poured into a spinning mold, which is rotated at a high speed during the subsequent steps. After the concrete is poured, the spinning mold undergoes a centrifugal procedure. The high-speed rotation of the mold helps to distribute the concrete evenly and remove any air bubbles or voids that may be present. This centrifugal action compacts the concrete and enhances its density, improving the overall strength of the spun pile. Once the centrifugal procedure is complete, the spun piles are subjected to steam curing. Steam curing involves exposing the piles to a controlled environment of high temperature and humidity, which accelerates the curing process. This rapid curing enhances the strength development of the concrete and reduces the overall curing time. After the steam curing, the spun piles undergo demolding, where they are removed from the spinning molds. Once demolded, the piles are subjected to water curing. The completed spun piles are then ready for quality inspection and testing. They are checked for dimensional accuracy, strength, and other required properties to ensure they meet the specified standards. Once the piles pass the quality control tests, they are ready for transportation and installation at construction sites. The manufacturing process of spun piles involves careful attention to detail and adherence to strict quality control measures. By following these steps, spun piles of consistent quality and superior performance can be produced. These piles play a crucial role in supporting various structures and foundations, contributing to the stability and safety of construction projects.
The manufacturing process of Ulterra's counterforce drill bit involves cutting-edge technology to combat drilling dysfunctions caused by lateral vibration. This innovative solution has been field-proven across more than 20 basins globally, demonstrating exceptional performance and drilling over 50 million feet of hole annually. The counterforce technology is designed to convert the vibrational energy generated during drilling into improved drilling performance. Traditional drilling bits are susceptible to damage due to downhole lateral vibration caused by the interaction between the bit and the formation. Ulterra's counterforce technology takes advantage of this energy and redirects it back into the formation, resulting in enhanced rate of penetration, ROP, and maintaining sharper cutters for extended periods. Counterforce achieves its performance by strategically positioning each cutting element for maximum efficiency while maintaining a continuous work progression across the cutter layout. This layout utilizes alternating degrees of cutter orientation, allowing the Counterforce PDC polycrystalline diamond compact bits to slice through the formation effectively. This design also enables the bit to maintain a secure grip on the bottom hole pattern, limiting destructive vibrations and improving tool face control. Consequently, the bit's lifespan and cutting efficiency are enhanced. The manufacturing process ensures that each counterforce drill bit offers high-performing cutter layouts, ensuring full hole coverage for increased durability. The engineering tolerances and force tuning are carefully calibrated to achieve optimal performance. The technical specifications of the counterforce drill bits encompass a size range from 4 inches to 28 inches, making them suitable for a variety of applications. The body materials of the bits include matrix and steel, providing a combination of strength and resilience. Counterforce bits are available in a range of cutter grades, accommodating all grades of deep leached cutters, which further emphasizes their versatility. These bits can be connected to different drilling tools and equipment through various connections, including 3.5 REG, 4.5 REG, 6 7/8 REG, 7 7/8 REG, NC35, North Carolina 38, North Carolina 40, and North Carolina 50. By effectively harnessing and redirecting the vibrational energy generated during drilling, Ultera's counterforce drill bits offer operators a solution to combat drilling dysfunctions caused by lateral vibration. Hydraulic fracturing, also known as fracking, is a modern technique used to extract oil and natural gas from deep underground reservoirs that were previously inaccessible. This process involves a combination of advanced drilling methods and controlled fracturing of the rock formations to release hydrocarbons. The procedure follows a systematic approach to ensure both environmental safety and efficient resource extraction. The process begins with the identification of a hydrocarbon-rich reservoir located deep beneath the Earth's surface. A surface hole is drilled downwards, well below any freshwater aquifers, which typically lie at a shallower depth. To safeguard these aquifers, an upper portion of the wellbore is drilled using a water-based mud system. This not only protects the aquifers, but also cools the drilling bit and carries away the cuttings to the surface. Once the drilling passes through the water aquifers, steel casing is inserted into the well, and cement is pumped into the casing. This cement creates a barrier between the well and the freshwater aquifers. Further drilling takes place, ultimately reaching a point where the hole turns horizontally within the targeted reservoir. This horizontal drilling can extend for thousands of feet. Protective casing is then inserted into the well and cemented in place, ensuring a barrier throughout the entire length of the well. After the drilling is completed and the casing is secured, the next phase, known as completion, commences. This involves installing a valve at the surface and preparing the wellbore for the perforating run. Perforating guns are lowered into the horizontal section of the casing and fired at specific depths, creating perforations in the casing and the rock. Subsequently, hydraulic fracturing takes place, employing pump trucks with immense horsepower to send a mixture of mostly water and sand deep into the wellbore and out into the perforations. This fractures the rock and keeps the fractures open with sand, enabling oil or natural gas to flow into the wellbore. This hydraulic fracturing treatment is performed in multiple stages, involving the use of plug-in perforating guns. These stages include pumping the fracturing fluid into different sections of the wellbore, each with their own set of perforations. Once the multi-stage stimulation is finished, the plugs are drilled out using a workover rig, allowing the hydrocarbons to flow up the wellbore. To complete the process, a permanent wellhead, or Christmas tree, is installed, allowing the captured oil or natural gas to flow and be collected at the surface. This marked the beginning of the sales process, where the extracted resources are transported for further processing and utilization. Hydraulic fracturing has revolutionized the oil and gas industry by enabling the extraction of previously trapped resources. When carried out with proper environmental considerations and responsible techniques, this process has proven to be an effective way to harness energy while minimizing ecological impact. The rig site drilling process at Patriot Energy in the Permian Basin of West Texas is a complex and orchestrated operation that involves multiple crew shifts working around the clock to achieve the goal of drilling a well to a total depth of about 8,100 feet. This process encompasses drilling, logging, and eventual preparation for fracking. At the core of the operation is the driller, the main authority on the platform. The driller manages the controls, maintains written logs, and oversees the drilling process. While there is limited verbal communication among crew members due to their high level of coordination, the driller ensures that the drilling progresses smoothly. The drilling rig is equipped with various components that keep the operation running. One essential aspect is the drilling mud. a mixture of fluids that serves multiple purposes, including lubrication and providing crucial insights into the well's condition. Mud engineers monitor the drilling mud's properties as it flows out of the well, enabling them to glean information about the well's state. A significant portion of the operation happens on the drilling platform. The rig's appearance and components are relatively standard across rig sites globally. The central action involves pipe spinning at a rate of around 45 to 50 revolutions per minute. The weight placed above the pipe applies pressure on the bit and maintains a consistent drilling process. Each section of drilling pipe is approximately 35 feet long and takes varying amounts of time to drill, depending on the type of rock being penetrated. As a section of pipe nears completion, the driller halts the process. This is when the rig floor team swings into action. The Kelly drive, a component that connects to the last section of pipe, is moved over and lifted to disconnect the pipe. The driller employs back pressure to unscrew the pipe. The Kelly drive is then positioned over the next section of pipe, which is stored in a mouse hole, a shallow Q-up hole on the ground. The pipe is raised to match the previous section, and tongs seal it securely. The master bushing, traveling block, and swivel are engaged, and the next section of pipe starts its descent. This process is repeated numerous times, considering that the well's depth requires around 230 sections of pipe to be drilled. Once the well reaches its final depth, a transition occurs. The well is flushed with circulating water for several hours, and then the entire length of drill pipe is pulled out. This paves the way for a logging crew to initiate a computerized analysis of the well. Probes and wires are connected to gather data from the various oil-producing zones. This data aids geologists in determining the well's viability for completion. The logging process, while intricate, sets the stage for the well's future steps. The subsequent phase involves replacing the existing pipe with a new set. This process is labor-intensive and time-consuming, requiring the movement of each section sequentially. This extensive effort ensures the integrity of the well. Following the removal of the previous pipe and the installation of new pipe, cement trucks arrive on the scene. The cementing process is meticulously coordinated and involves connecting hoses and pipes. Once prepared, a substantial pumping operation begins, propelling a mixture of cement and water down the well. This encases the production pipe securely in place. The entire operation at Patriot Energy's rig site exemplifies the dedication and collaboration of the crew members who work tirelessly to extract American oil from the soil of the Permian Basin. It's a testament to the intricate processes that underlie the energy industry's advancements and contributions to modern society. At its core, the SIM induction bending machine comprises a single induction heating coil and strategically positioned conductor units. These conductor units encircle the pipe or tube to be bent, creating a symphony of heat distribution that orchestrates precise control over the bending process. The strategic placement of these conductor units guarantees consistent heating and uniform bending along the entire length of the material. Operating with finesse, the machine generates a high-frequency electromagnetic field through its induction heating coil. This field penetrates the material, inducing heat and rendering it malleable, ready for the bending ritual. The conductor units, in harmonious coordination with the heating coil, ensure that this heat is evenly distributed, culminating in bends characterized by their uniformity and minimal distortion. The advantages of the SIM induction bending machine are manifold. It enables the production of complex bends, boasting tight radii and precise angles, pushing the boundaries of what is achievable. Eliminating the need for welding or mechanical deformation drastically reduces the risk of structural weaknesses or defects, instilling confidence in the integrity of the bends. Moreover, the machine enhances productivity and efficiency through its advanced control systems and unmatched bending precision. Two primary methods are typically employed for this purpose: induction heating and open flame heating. Induction heating utilizes electromagnetic fields to heat the pipe uniformly and efficiently, while open flame heating relies on direct exposure to flames. The key to success in the hot bending process lies in achieving and maintaining the pipe at a specific temperature. This temperature varies depending on the type and thickness of the steel. Once the desired temperature is reached, the heated pipe is meticulously bent to the desired angle using specialized equipment like bending machines or hydraulic presses. Typically, two primary methods are employed for this purpose: the use of a saw or a cutting torch. The choice between these methods depends on factors such as the material's thickness, the desired accuracy of the cut, and the overall project requirements. Regardless of the cutting method used, precision is paramount. The cut must be made precisely at the desired length, often based on project specifications or customer requirements. Any deviation from the specified length can lead to issues with the fit and function of the bend, potentially compromising the overall integrity of the project. The dimension check is a critical quality control step in the manufacturing process of bent steel pipes. After the bend has been accurately cut, it is essential to ensure it adheres to the specified dimensions. This involves a meticulous comparison of the actual measurements of the bend with the precise values outlined in a dimension check table. Heat treatment is a vital phase in the manufacturing of bent steel pipes. This process serves to optimize the mechanical properties and structural integrity of the bend. It typically entails heating the bend to a precise temperature and subsequently subjecting it to controlled cooling. Magnetic testing, often referred to as magnetic particle inspection, MPI, is a crucial non-destructive testing, NDT, technique employed to meticulously assess the integrity of a bend's surface and near-surface areas. This method excels at detecting imperfections, such as cracks, fissures, or irregularities that might undermine the overall structural soundness of the bend. The magnetic testing process begins by magnetizing the bend, typically using a strong electromagnetic field or a permanent magnet. Once magnetized, iron particles or magnetic ink is meticulously applied to the surface of the bend. These particles are drawn to areas where magnetic field lines converge or are disrupted due to surface defects. Under suitable lighting conditions or with the aid of specialized equipment, any defects or anomalies in the bend's surface become readily visible. This method allows for the precise identification and assessment of discontinuities, ensuring that any potential structural weaknesses are detected and addressed promptly.